Let's continue our study of flip-flops by introducing the D flip-flop, which is also known as the data flip-flop, and D flip-flop is a slight modification in the SR flip-flop. So we are just going to modify our SR flip-flop. So it is a slight modification of SR flip-flop. In the previous tutorial, we have already studied about the SR flip-flop, and here is the circuit diagram and the characteristic table of the SR flip-flop. So let's see what the slight modification will be. So we are going to modify this circuit diagram and the characteristic table so that we can ignore some undesired conditions. So if we take a look at this characteristic table of the SR flip-flop, you can see that if you consider these two conditions, you can see that when the value of S is equals to 0 and value of R is equals to 0, or you can say that if S and R are both having low voltage, so the excitation state or the next state after the clock transition will be equal to the previous one. So in that case, we call this as memory because the flip-flop has maintained its previous state. If we consider this condition here, so when the value of S and R will be equal to 1, then we can say that we cannot determine the next state of the flip-flop. So these two are the undesired conditions. So let's focus on these two left out conditions here. You can see that in these two conditions, we are actually changing the state of the flip-flop. So if the value of the reset is equals to 1, then the state of the flip-flop is cleared to 0. And similarly, if the value of set is high, then the state of the flip-flop will be equal to 1. So you can see that in these two conditions, the value of one input is actually the complement of the another. So you can see that the value of R is actually the complement of S. So why not combine these two input signals into a single signal? And we can do that by introducing an inverter gate. And we know that inverter gate is used to invert or to complement the given signal. So we can use an inverter gate and we will connect S and R to a single input. So we are going to call the single input as D. We will call it as D, which is also known as the data signal. So if you can see that the value of D can be 0 or 1. So let's consider the first case when the value of D is low. So when the value of D is 0, the value of S will be 0 and the value of R will be the complement of S. So the value of R will be 1 and S is equals to 0. So in that case, you can see that this condition will get applied. So if the value of D is high, then similarly the value of S will be high and R will be the complement of S. In this manner, you can see that we have introduced a single signal, or we can say a single input, and this basically reduces these two undesired conditions. We do not want this condition and this condition in the data flip-flop. So data flip-flop is basically storing the data, and it is storing the data by maintaining the state to 0 and 1. So this is our D flip-flop. So this is the circuit diagram of the D flip-flop. This is the circuit diagram of the D flip-flop, and let's make the characteristic table of the D flip-flop, which is very easy. First we are going to write, because there is only one signal, we are going to write D here. So I will write D here. And we know that the value of D can be either 0 or 1. So now when the input supplied to the circuit, which is D, is 0, then we know that the value of S will be 0 and value of R is 1. So in that case, the value of Qt plus 1 will be equal to 0. And similarly, this will be equal to 1. So this is how we draw the characteristic table of the D flip-flop. So I'm going to write here, this is the characteristic table of D flip-flop. In the next tutorial, we are going to study the JK flip-flop. So we will understand the JK flip-flop in the next tutorial. So that's it for this tutorial. Thanks for watching.